Welcome to part 2. I will continue to work on ways to try to make these, I don't know that I can make them interesting, but I'll try to keep them short. So here we go. We have a new kind of function called a power tower. And a power tower is just a function raised to another function. And when we're looking at these power tower functions and taking limits of them, they can yield 3 more indeterminate forms. So that's the end of it. We have 5 total indeterminate forms that we can look at beyond that can all be changed back into 0 over 0 or infinity over infinity. These 3 functions, we're all going to use the same trick. And our trick every single time is to, instead of looking at the limit of the power tower function, we're going to say, you know what, I'm going to change the function and solve an easier problem and then go back to the original situation. So instead of, just looking at the function, we're going to look at the log of the function, because that's going to help us get this into the form of 0 over 0 or infinity over infinity and find that limit. The only thing we have to do then at the end is make sure we solve it back and say that we didn't solve for the log, the limit that they wanted. We have to get that limit back by taking e to the l. So let's see how this works. So real briefly, this kind of gives you the version of how you can get it into a better form. And how it's going to work every single time is by changing it into infinity times 0. So let's just look at this function and say, instead I'm going to analyze the function ln of x raised to the x squared function. We have log properties. That turns into x squared times ln of x. And now we're looking at the limit of that as x goes to 0, and we get 0 times negative infinity. We know how to deal with that because every function of this form can easily be changed into a ratio of 0 over 0 or infinity over infinity. And so we have some choices. We can make it ln of x over 1 over x squared, or x squared over 1 over ln of x. I don't want to do 1 over ln of x. Let's look at this. ln of x over 1 over x squared. Plug in 0, we get infinity over 0, infinity. We're ready to go. We can L-hop that. So that's going to be equivalent to the limit, as we go to 0, of 1 over x over negative 2 over x cubed. You'll get quick at taking these reciprocal derivatives. We're going to simplify that. Division is the same as multiplying by the reciprocal. So when we do that, we're at x cubed over negative 2x, x negative 1, let's make it negative 1, over 2x squared. Limit of that as x goes to 0 is 0. But we didn't answer the question they wanted us to answer. This is the limit to the question ln of x to the x squared. So to get our answer back, we have to solve for our power tower function. So our limit is actually equal to e to the 0. So the limit of that is 1. And I just noticed this really should be a x going to 0 from the positive side. We should, oh, I guess we don't, yeah, we should identify that. Okay, so let's take a look at another. We look at this, the first thing we're going to do is plug in zeros. We go from the positive side. Let's see, that's going to explode up to positive infinity, to the sign of 0, 0. Oh, we know that's one of our forms. let's take the logarithm of it, because then we know we can use log properties to help us. So instead, we're going to look at ln of 1 over x to the sine x. Log properties, sine x times ln of 1 over x. We look at that as x goes to 0. We're at 0 times ln of infinity. Infinity, 0 times infinity, that's good to go. Well, let's think about this. Which one would we want in the denominator? Boy, this looks rough, but let's recall more log properties and know that that's the same as negative ln of x. Well, that helps a little bit. Let's do this. Let's put the logarithm in the top. So we're at negative ln of x over 1 over sine x. And we can just chain rule this. So we check first. When we evaluate this at 0, we're at infinity, 1 over 0, infinity. Yeah, we're good to go. We can L-hop it. So we're at the limit as x goes to 0 of negative 1 over x over, let's see, think of this as sine x to the negative 1. So negative 1 over sine squared x times chain rule cosine x. And this one's kind of long, so let's look at simplifying this fraction first. So again, let's see, the negatives are going to cancel. This division is multiplication by the reciprocal. So we're really looking at the limit as x goes to 0 of sine squared x over x cosine x. Plug in 0. 0 over 0. Oh, got to go again. So derivative of sine squared to sine x, cosine x, little product rule, cosine x minus x sine x, plug in 0. Let's see, the numerator is 0 times 1, denominator. Ooh, the denominator is non-zero. Yay, we're done. Because 0 over 1 is 0. But don't forget, we have to solve back, because we solved a different question than we were asked. So the answer to our question, whoops, what just happened, is ln equals 0, because we need to find out what the limit of this business is. So e to the 0 is 1. Oh, that means this limit is 1. Let's try one more. Oh, if I can erase some stuff, give myself a little bit of room here. So let's try one more and see what we can do with this. So we plug in 0, we get 1 to the 1 over 0, infinity, oh, 1 to the infinity. We're ready to do a log. So let's, instead of answering their question, we're going to answer the question about the limit of ln of, excuse me, 1 plus x to the 1 over x as x goes to 0. That's going to help us because we can use a log property. So we're at 1 over x, ln of 1 plus x. We plug in 0, we're at infinity times ln of 1 is 0. Oh, we're good to go, and this is an easy choice, right? Because we just throw that x in the denominator. So really we're looking at the limit of ln of 1 plus x over x as x goes to 0. And again, we really should be doing 0 from the positive side. And we check it out. Let's see, we're at ln of 1, 0 over 0. Yeah, we're good to go. We can L-hop it. So we're looking at the limit as x goes to 0 of 1 over 1 plus x over 1. limit as x goes to 0. Oh, that's just 1. Oh, that's nice. But don't forget, we didn't solve the question they asked us. We solved the question of ln of what they asked us. So to get back the answer to what they asked, we have to solve for this interior argument, and we get that limit as x goes to 0 of 1 plus x to the 1 over x equals e to the 1 t. So I know these things go kind of quickly, but you can stop and start them, but really there's a lot of review from Paul's and Khan Academy, but these are the tricks that over the years are the best ones to solve it. So recapping quickly, if you've got a power tower, you've got no choice. You need to use a log. Go back a step. If we've got infinity over infinity, or infinity minus infinity, excuse me, one way to deal with that is hopefully a common denominator. There are a few other tricks. This is kind of the trickiest one. But the one that comes up the very most on the AP test is the idea of using log properties to better analyze what those logarithms look like. And the other form that is easy to deal with is infinity times 0, because these guys are reciprocals of one another. So it's just a matter of lining them up in a way to either get 0 over 0 or infinity over infinity. And you have some choices. So make your life easy. Keep your chain rules as easy as possible. And at every step, be sure you take a look back and simplify your fraction. So don't leave any complex fractions. At every single step, simplify it into one fraction, one ratio, and you can recheck and see if you're still at 0 over 0 or infinity over infinity. So that is our LHOP for today. And we won't spend a lot of time on limits. They're going to come up in context. And hopefully they've just piqued your interest at a little bit of all the different ways that infinity can behave.